So I think in my abstract I might have mentioned Kac-Moody two categories, but that turned out to be unrealistic, I discovered. So I'm going to try and show you today Heisenberg categories, which are a little easier to explain, but actually I know rather less about them. So we'll see how it goes. So let's first of all do a little bit of theory. So all the theory for today is right at the beginning, and then it's just examples. So let C be a monoidal category. And M be any category. And I want to tell you what it means to say that M is a C module category. So you can probably guess what that is. So you want to have a functor, tensor, from C cross M to M, and that should be associative and unital, but like with the definition of monoidal category, it needn't be a strict module category. You need an associator and unitor, and the axioms, which, as you know, I never write them down. Okay, but it's equivalent. Exactly, I'm saying that M is a C module category, it's exactly equivalent to having the data of a monoidal functor from the monoidal category C to the monoidal category that we finally get to write up again from the very beginning of the first talk, of endofunctors and natural transformations of C. So in practice, if M is a C module category, what it allows you to do is it allows you to take some picture representing some morphism in C and interpret it as a picture representing some morphism here. In other words, some picture of a natural transformation between some endofunctors of the category M. Okay, so in practice, when you do this, you just think of pictures of morphisms in C straight away as pictures of morphisms here, so pictures of natural transformations between endofunctors of the category M. Okay. So for example, let's just sort of see what sort of things you can do. If M is a C module category, there's an induced algebra homomorphism by this functor from the algebra end C of the unit object to the algebra, I guess I'm going to write it end, oh, this looks really bad, end in the category end M of the unit object here. Let's maybe not write that. I mean, what was the unit object here? It was just the identity functor from M to M, and this is just the algebra of all natural transformations from the identity functor to itself, right? It's the algebra of all endomorphisms. Let's just write it in words, because that looks terrible. Endomorphisms of the identity functor from M to M. That's an algebra. That's so whenever you have a module category, you get this induced algebra homomorphism. So this has a name. Called the center of M, and usually just denoted Z of M. It's exactly that algebra of endomorphisms of the identity functor. Okay. Just to make sure that you see why that's called the center of the category M, if M is just, so if we're basically in that case when the category M was a one-object category corresponding to an algebra A, or it's pretty much the same as talking about the category of A modules for an algebra A. That would be the kind of abelian envelope of that guy. Then the center of the category M, natural transformations from the identity functor to the identity functor, is exactly the usual center of the algebra A. And that you just a natural transformation alpha from the identity functor to the identity functor, you just kind of take what that natural transformation does on the regular representation. So that's now and you just evaluate it on the unit in the regular representation, and that gives you actually always an element of the center, and that's an isomorphism.
The center doesn't depend on C?
Center doesn't depend. No. This is just a purely M definition here. Okay, but I've observed in particular there's this map from this guy, which you might call the center of C, if you like, to the center of M. So there's this algebra homomorphism. It's even a little bit better than this. I'm now really going to bring C in. Remember last time we had, so here's the center of the category M. This is actually a module Last time we discussed the trace of the monoidal category C, which was an algebra. The center of this module category M is actually a module over the trace of the monoidal category C, providing C is pivotal. That's essential, and you'll see right away when I explain how this goes why you need C to be pivotal. So remember how I was drawing trace classes here? I had this kind of funny non-mathematical picture of the trace class of a morphism F from X to X in the monoidal category C. So that was its image in the trace of this category C, and we're trying to act on something in the center of the category M, right? So that's a natural transformation from the identity function to the. How would you draw that? Well, I would just draw that as a bubble. If alpha is the natural transformation, I would just kind of have a coupon with alpha in. This is a picture of that natural transformation from the identity functor to the identity functor. So this is a picture in end M here. This is just how I draw natural transformation, an element of the center alpha. It's like a bubble labeled alpha. And we're trying to act with something on the trace, on something in the center. And so you will know what I'm going to do now. I just put that coupon in that hole that was crying out to. Oh, no, that doesn't make any sense, right? So I've got to use the pivotal structure here. At the moment, this picture looks like a picture in C, and this was X, and this would have been the right dual and the left dual, and that cup and that cap are these adjunction maps in C coming from the pivotal structure. Remember, there was this thing called B sub X that was this isomorphism here. And now what I'm doing is I'm thinking of that picture, which was a picture of a morphism in C. I'm just thinking of it using the action. I'm just thinking of it as a picture actually of of a natural transformation in between functors on M. Right? And then it makes sense just to stick this in. This is now all a picture in end M, and now it's a morphism from the unit object to the unit object. So yeah, that's a new element of the center of the category M. Okay, so everything's set up nicely so that this actually makes the center of M into a module over the trace of C. Okay. So it's a simple idea, but it's actually rather powerful and useful, and I think there's many more situations where this simple idea should be applied, actually. The rest of the talk, I'm going to just show you kind of a simple example to just illustrate this powerful idea. So now we've got to go back to where we were yesterday. You remember we had this oriented Brauer category. So I think this might look familiar, roughly. So I'm going to take the monoidal category C to be oriented Brouwer, and I'm going to take the module category M, this M in this general theory here. So that's just some category. Actually, I think I'm just going to tell you mainly about P equals 0, but I'm going to take whatever your favorite category of representations of GLN is. And I just thought I may as well just take all modules over the universal enveloping algebra of the Lie algebra GLN. Okay, so this is the universal enveloping algebra of the Lie algebra GLN. I'm probably over the complex numbers. I'm just looking at all modules over this. Okay. But I mean, my favorite thing to put in here is actually this Bernstein-Gelfand category O for the Lie algebra GLN. Your favorite might be, I don't know, to put rep GLN, rational representations of the group. But the important thing is I'm not thinking of this as, this happens to be monoidal. That's not the point here. I've kind of, the monoidal category is the C, and this I'm not even thinking about the monoidal structure over on M at all. Okay, I'm just interested in this abstract category. Okay, so hang on, let's go over that a little bit. So I'm lying to you a little bit. I've dropped the delta. The oriented Brouwer, remember, it had these generating objects up and down, and this crossing, and then the rightward cups and caps, which said the down was right dual to up. And those were the relations, right? They look pretty familiar. And then I defined the sideways crossing, and I declared that that was invertible. And then the leftward crossing was the inverse of that. And then I defined the leftward cup and the leftward cap. And I had one more relation about the bubble. I've thrown that away. I haven't got that relation. It's just OB, not OB of delta. But you remember from last time it was pivotal. It's still pivotal when I drop that relation. Actually, what I'm going to do is I'm going to take a slightly different monoidal category called the affine-oriented Brouwer category. And to get that from the oriented Brouwer category that we saw before, I'm going to add one more generating morphism, which is just a morphism from up to up. And the picture for it is just putting a dot on that strand. Okay? And there's one more relation, which is this crazy-looking relation. And I'm about to tell you where this crazy-looking relation comes from. It tells you how to move the dot past the crossing. And you can basically move the dot past the crossing, but you pull up an error term, which is an identity here. Okay, so I've just added a new generator, a new relation. The first amazing thing is that this is still pivotal. Remember, this is why I needed these leftward cups and caps, because that made the down also a left dual of up, and then the left duality function and the right duality, this B was just the identity, and it was pivotal before. It's still pivotal. Let's just think what's the content of that briefly. I've got to show that basically the left dual of this new morphism is equal to the right. No, I got this long way around, didn't I? I've got to show that the right dual of this new morphism is equal to the left dual. And the right dual, by definition, is that picture, and the left dual, by definition, is let me try and do this. That picture. So the new content on top of what we already knew about oriented Brouwer is I've got to show that for this new morphism, the right dual of this morphism is its left dual. So you have to verify that relation. I'm not going to do it, but it's a relation chase. It really needs to be checked to see that this bigger category is pivotal. So maybe I just erase that since I'm not going to do it. So this is affine-oriented Brouwer, and I'm telling you that this new category, that representations of GLN is a module category over this slightly bigger category. So now I've got to tell you how. So I've got to tell you which endofunctor of representations of GLN up is when you apply this monoidal functor that's our action. And it just maps to the endofunctor that's tensoring with the natural representation of GLN. That's V, the natural GLN module. Okay, that's an endofunctor of GLN modules. Okay? And down is tensoring with the dual. So this is particularly nice in category O. These are kind of projective functors and let me see, I need to say what all the morphisms go to. Well, hang on, tensoring with V star is adjoint to tensoring with V. So that's what the cup and the cap go to, right? They're just the kind of canonical adjunction there. So I've told you what cup and cap go to. What does this guy go to? So this is a morphism here. So it's got to go to a natural transformation between this functor done twice. Right, so this is up tensored up. Up tensored up goes to just tensoring with V and tensoring with V again. I need a natural transformation from that functor to itself. And there's an obvious one, just flip the tensors. Okay? And you all know that satisfies those relations. So that's where the crossing goes to. It just goes to that endomorphism of V tensor blank. And where does the new morphism dot go to? So this is meant to go to this is meant to go to this is meant to be a natural transformation from the functor V tensor blank to the functor V tensor blank, and this just goes to multiplication by this magic element Eij tensor Ej. Those are the matrix units in the Lie algebra GLN. That's the Casimir tensor. And multiplying with the Casimir tensor defines you a GLN module endomorphism. So this Eij, remember this is a functor, so you can put in any module there. This is a natural transformation. This Eij is acting on the V. This Eij is acting on whatever module you've put there. Okay, that's an endomorphism of that functor. And this bizarre relation here is a little calculation. It's a good one to do, to see that this is something totally natural, and you calculate the relations between this Casimir tensor and the tensor flip, and you magically find that relation. This is known as the degenerate affine Hecker algebra relation in this game. Little d for degenerate. Okay, so well, that's a little bit of stuff. So here's an example of a module category over a monoidal category. Okay. So I'm not going to do a whole lot with this, but I thought it would kind of get you into this game a little bit. We saw this oriented Brouwer yesterday. For example, I said that in this situation there's always an induced algebra homomorphism from the center of the monoidal category to the center of the module category. Let's just think about that. Let's use this example to illustrate that idea. What is so let's think about what is what is the center of this affine oriented Brouwer category. So these are just this is actually just so there's some theory in here that I'm not telling you about, but it turns out that remember, so endomorphism, so that's diagrams which are empty at the bottom and empty at the top. So you only have bubbles, and you can do all sorts of bubbles with all sorts of dots on. But it turns out you can simplify all bubbles just into these counterclockwise bubbles with some number of dots on them. And it turns out these then actually are algebraically independent. So it's just this polynomial algebra in these simple. In fact, the right way to think of this is it's actually the algebra of symmetric functions. And these bubbles, you should think of them as being the elementary symmetric functions. Remember, the algebra of symmetric functions is free on all elementary symmetric functions. And if you're kind of bugged by where the clockwise dotted bubbles went, if you have a clockwise dotted bubble with n dots on it, that actually goes to let me see, there's no dots, that's E1. This is the complete symmetric function. E is the elementary symmetric function, H is the complete symmetric function. They also give a system of algebraically independent generators for the ring of symmetric functions. And those clockwise dotted bubbles basically are the complete ones. And so there's a little theory in here. You have to because elementary and complete symmetric functions, they're not independent, there's a nice relation between them. And you have to verify that indeed these clockwise and counterclockwise dotted bubbles satisfy that famous relation between elementary and complete symmetric functions. And that's another fun exercise. It's like all of symmetric functions are living in this, this example. Sometimes. The thing is, the ring of symmetric functions appears in all of these examples, and in some of them that's very important, and in some of them that seems to be unimportant. And from this trace perspective, I haven't worked out why they're important. From the K-naught perspective, they're usually the irreducible objects in these categorifications. But okay.
Sorry, so you said these are the elementary symmetric functions?
Yep.
Where the elementary symmetric functions are?
So this is this algebra of symmetric functions, which you can define by introducing some auxiliary variables called x, and thinking of this as an inverse limit of genuine symmetric functions in those auxiliary variables x. But at the end of the day, this is just by itself an algebra that's freely generated by these e's, so they're just symbols now. I don't see the, okay. Okay, so that was, so, and we need to think about what's the center of this GLN modules on the other side, right? Because we're meant to be having an algebra homomorphism from this to the center of U of GLN mod. That's our category M, right? Oh no, but that's just modules over an algebra, and I already told you that that's the center of the algebra, and I'm not going to say very much about the center of this enveloping algebra. I'm sure everybody is good on that. But let's just write down the formula, which is kind of another great exercise. If I take the bubble with n dots, what central element in the enveloping algebra of GLN does it go to? And this is just an exercise in chasing definitions. But you get this nice element. I'll write it down. And that's sum of monomials in the matrix units in the enveloping algebra, and that's central. So it's like lots of kind of fun things going on. Okay. That's bad. You're right. That's totally bad. All these n's mean different things. I think I'm not even going to try to fix it. Okay, good. So let's not dwell on this example too much, and show you the example I really wanted to do, which I think this is a good lead-in to it. So this affine-oriented Brouwer, AOB, I didn't realize it when I first came across the affine-oriented Brouwer, but actually it should be called Heis 0. It's actually the Heisenberg category of central charge 0. And what I actually want to do is tell you about the Heisenberg category of central charge -1. So that's my final goal, is to tell you about that. I think I need to talk about the word Heisenberg a little bit. So let's do that. Again, I think I'm going to tell you the story as though the field was the complex numbers. But I'm going to have like modules over symmetric groups showing up in a little bit. So again, I'm going to just talk about modules of the group algebras of symmetric groups over the complex numbers. But everything actually works over any field, and it's very interesting. The thing that is just you have to work harder is instead of having the universal enveloping algebra of this complex Lie algebra, you have to pick the right Z form in this universal enveloping algebra to reduce mod P before the things I'm saying are correct. And honestly, I think I know what the right Z form is, but it's like somehow the people pursuing this don't care. So, I feel like we should all care about doing this properly over Z and getting it, and these beautiful ideas. There's just tons of mileage in this. Let's have a go. Anyway, so this is a Lie algebra H. So this is the infinite dimensional Heisenberg algebra. And I've just given a presentation for it. It's generated as a Pn and Qn for positive integers n, together with C, which is, of course, going to be central. And the relations, basically, everything commutes except Pn and Qn, when their commutator is n times the central element C. Okay, so can you sort of swallow that? So these are the Lie bracket relations for this Heisenberg Lie algebra. Okay, is that good enough? So think about the p's as being like the positive part, and c is like the diagonal part, and the q's are like the negative part of this Heisenberg Lie algebra. Then I can take the universal enveloping algebra of that Lie algebra, call that U of H, and if I have some, for me always integer k in mind, I can specialize the universal enveloping algebra at central charge k. So I just factor out that the ideal generated by C minus K, and I'll just call that. So that's kind of Heisenberg at central charge K. That's the guy that we're interested in. Okay. So let me just tell you what. So as I said, I'm really interested in the case -1 from now on, but you can do this for any integer k. And actually, this guy here has to do with a case k equals 0, which is somehow the boring case from the Lie theoretic point of view. But let's do k equals -1 now, because that's suddenly more interesting from this point of view. Then there's something called the Fock space representation of this Heisenberg Lie algebra. So this is sort of like a Verma module or something like that. But I'm just going to factor out a left ideal to get a module over Heisenberg. This is my symbol for left ideal. I just made that up. So I'm going to take the left ideal generated by, well, I want C to be -1. So I guess I'm factoring out the left ideal generated by C plus 1. And then I'm going to kill all the Q's. So if you're thinking of the Q's as the negative things, this is sort of the, maybe you Verma modules are high. This is like lowest weight. Okay. And so in here you have the image of 1 in the universal enveloping algebra. That's usually called the vacuum vector. I mean, by the PBW theorem, this is like a Verma module. It has a basis given by PBW monomials in the p's, but the p's all commute. So this, as a vector space, I'm even writing C. Look, as a vector space, it just looks like the polynomial algebra on the p's. Okay, which that's a little bit like symmetric functions again. And the vacuum vector, that's like the 1 in symmetric functions. And then when you're meant to sort of think that this is some sort of energy of some particle that's getting, and the p's are kind of exciting this particle. So the vacuum is kind of no energy. And then as you hit it with p's, the energy goes up. And that's why I always think it's more natural to work with the lowest weight construction here. And so that's a simple. So in fact, this is always an irreducible, faithful representation of Heisenberg. This Fock space representation. Okay. So now let's go back. Now we've got some interesting Lie theory on the board. Now I want to tell you what. So let me see. So just earlier I told you about affine-oriented Brouwer, and we were kind of getting used to those relations. And I said that was like Heisenberg of central charge 0. That was the Heisenberg category of central charge 0. And now I'm trying to tell you about the Heisenberg category of central charge -1. Okay, and that's going to have to do with this central charge -1 specialization of Heisenberg. Okay, I feel like I'm going to tell you. So I'm going to define this new guy. In fact, there's a monoidal presentation of Hei's k for any integer k. They all look very similar. You've already seen k equals 0, and now I'm just going to quickly do k equals -1. But there's if I was trying to be quick, I'd do them all at once at the beginning. Let's get rid of that. I'm going to have a modular category that it's going to act on in a little while, but I'm not going to tell you what it is. I want to tell you what Hei's -1 is. So this definition is due to Kovanov. It's usually called Kovanov's Heisenberg category. You know how it's going to go. I'm going to give you its presentation. Okay? But you should be thinking about these sort of oriented Brouwer-like pictures. It's just the relations are going to be different. So generating objects, up and down. Generating morphisms, crossing, right cap, dot. Relations, okay. So remember, these were the symmetric group relations. I'm going to keep them. And this was this degenerate affine Hecker algebra relation. I'm going to keep that. Of course, I want to be saying that the down is right dual to the up. Basically, this is what you get when you kind of adjoin a right dual to the degenerate affine Hecker algebras. So that's where we are so far. But now things are going to change. It's this last two that are different. Here, before we said that was invertible, right? That goes from up, down to down, up. And saying that it's invertible is saying that it's an isomorphism. So, that's, I don't know, at the level of like the Grothendieck ring or something, that's saying that up and down commute when you pass to K0. You should think of them as being like P1 and Q1 in Heisenberg. And for Heisenberg of level 0, yes, P1 and Q1 commute. But now we're doing Heisenberg of level -1. So we don't want P1 and Q1 to commute. We want, what do we want? We want P1, Q1 minus Q1, P1 to be -1, right? If we're doing central charge -1. So that's not good because that's got minus signs in it. Let me try again. Okay, now I've got plus signs everywhere. So what I'm going to do is I'm going to put in a relation here about some morphism which is going from, for up, you want to, this is very confusing what I'm doing because I'm just, at least in K0, this P1 is like the isomorphism class of the symbol up, and Q1 is the isomorphism class of the symbol down. So this is up, down, direct sum, the unit object goes to down, up, and I want these to be equal in the Grothendieck ring in K0. So I want to have some isomorphism between them, and that's what I'm about to write down. I'm about to write down some morphism is invertible. It's just now this is a morphism in the additive envelope of this category, so it's a matrix of morphisms, and this matrix of morphisms is a 2-by-1 matrix, so it goes from a column vector of height 1, a column vector of height 2 to a column vector of height 1, and this object, this is this column vector of height 2, this object, and you see at the bottom of that it's up, down. At the bottom of that, it's the unit object. And this morphism goes to the top object, which is down, up, everywhere. And so that is indeed a morphism in the additive envelope between those guys, right? And my relation is simply that is invertible. Okay, that's it. That's this Heisenberg category. And hopefully I've explained it in a way where you see I'm basically just kind of forcing this very simplest Heisenberg relation to hold. Let's do what we did before. Let's name the inverse. Right, so this guy here is invertible. Let's name its two-sided inverse this leftward crossing and this leftward cap. So this is a matrix, this is a matrix. If you times these matrices together either way round, you get the identity matrix. Okay, so saying that that's invertible is saying there are some new morphisms which are the matrix entries of its inverse, and I'm just naming those new morphisms there. Okay. So I already have now, I have a leftward crossing and I have a leftward cap, and I guess I want a leftward cup, which I seem to remember is actually magically that weird element there. So that's the leftward crossing, the rightward cup, and then you need to sneak a dot in there. That's just, remember that these were shorthands. So these two guys are shorthands for the entries of the inverse matrix. This leftward cup is a shorthand for that guy. So, it's a little bit of magic goes on here in these relations. It seems so childishly simple. But the first thing, of course, you have to do is check that my leftward cup and leftward cap make down into a left dual of up so that it's rigid, and then you have to check that it's pivotal. It is. And, it's kind of a very fun calculation, and it's just pictures, but it takes, 5 or 6 pages to go through the details, because it's surprisingly long and not such a triviality.
Do you have to check that somehow these relations are not contradictory, or?
You absolutely do. For example, earlier on when I told you what end in affine-oriented Brauer of the unit object was, and I said this was just symmetric functions, there was some non-degeneracy statement in the background there. It's easy to check the relations, but you have to prove basis theorems for the morphism spaces. Otherwise, you've just done some nonsense. But and I've decided to not tell you about any of those. But all of these morphism spaces have basis theorems. They will have some sort of basis which is like, I don't know, reduced words or something like that, and you have to prove them. And of course, you prove them by finding some sufficiently general bunch of module categories where you can check that they're linearly independent. Okay, so that's good. I've told you what the -1, what Kovanov's Heisenberg category is. Does the definition make sense? I mean, you have to work with this for quite a while to get used to these relations. It looks innocent, but it's a subtle and not. Let's maybe. Does this one go up? Yes, it does. Let's maybe take a couple of minutes just to try to parse that definition, because it's kind of mean. Is this thing that this matrix is invertible that is saying quite a lot. Let's multiply some matrices. So I'm saying that this morphism in the additive envelope, and this is composition. I'm just going to write it like I multiply matrices. Remember, composition is actually stacking on top. So, and this guy here, and the other way around. Have to be identity matrices of the appropriate size. That's exactly what that's saying. So this one, this multiplies, it's a 1-by-1 matrix. And what 1-by-1 matrix is it? So I've got to put that on top of there plus that on top of there. Okay, so can I do it? And that's meant to be the identity morphism, which is that guy, because it's a morphism from down up to down up. So that is kind of, I'm expanding what this relation of saying this is invertible means. It means actually that relation. And here, okay, here it's genuinely a 2-by-2 matrix, right? And so I've got to put that on top of that. So that's hopefully that guy, which should be a different thing than that guy. It is, that's good. And then I've got to put that on top of the cup. and then I've got to put that on top of the crossing, and then I've got to put the cap on top of the cup. This is meant to be the identity matrix. Okay, so I'm expanding that definition. And so in this corner, it should be the identity morphism from up, down to up, down. That's that picture. And in this is going from the unit object to the unit object. So this is just the unit object. So that's actually 4 honest relations in the category Heisenberg -1. That one slick relation in the additive envelope, it's really the 4 matrix entries are equal. You see how, it's, maybe that's helpful, I don't know. So we've got some relations. Okay. So let's see if I can come back to Kavanov's Heisenberg category. And now, of course, what I want to do is come up with some nice module category over Kavanov's Heisenberg category. And the module category that I'm going to take is my kind of second favorite module category. I showed you my first favorite module category representations of GLN already, but this happens to be my second favorite. Can I use N? Is N okay? I don't know anymore. I think I'm going to use N, but I might get in trouble. No, that. So I want to take the direct sum of K Sn mod. Sn is the symmetric group. And I'm just going to take the direct sum of all the categories of Sn modules for all n. Okay? And so I claim that representations of all symmetric groups is a module category over this Kavanov's-Heisenberg category. Okay? So again, we've got to do what we did before. I've got to give you up and down, they've got to go to some endofunctors, and then the generating morphisms have got to go to some natural transformations between those endofunctors, and then you have to check the relations. So let's go ahead and see if we can do that. So it's not going to be those. Those guys commuted. Tensoring with the V and tensoring with the V star commuted on the representations of GLN. That was because it was level 0 Heisenberg. Now, these up, down, and down, up don't commute. They are. So I'm going to send this, of course, to induction from Sn to Sn plus 1. So the up arrow is induction. And we're doing all n at once, so it's the direct sum of all n of all the induction functors. And the down arrow, of course, is restriction. And, of course, induction's tensor, that's left adjoint. So, restriction is right adjoint to induction, and that's exactly these rightward cups and caps, this relation here. So the rightward cups and caps are going to just go to the canonical adjunction between induction and restriction. And then that relation is just saying that restriction is right adjoint to induction. So we're good on that relation. But I still need the crossing and the dot. So the crossing is a natural transformation from induction squared. So that's induction from Sn to Sn plus 2, right? So that's tensoring over Sn with the group algebra of Sn plus 2. It's tensoring with that bimodule. To get a natural transformation of induction squared, I basically need a bimodule endomorphism of that bimodule. And there's a completely obvious one. I can just multiply on the right here by the last transposition. Right, so this is my bimodule that I'm tensoring with. It's an Sn plus 2 Sn bimodule. Right multiplication by that last transposition is a bimodule endomorphism. So that gives me a natural transformation of that functor. That's my crossing. Okay? And I think it's immediate that these relations hold. Okay? And I'm nearly there. I've got to tell you about the dot. So this is meant to be a natural transformation just from induction to itself. So now I just need an endomorphism of this bimodule. as an Sn plus 1 Sn bimodule. And again, I can just kind of multiply in that tensor slot there with, is it going to fit? Well, hopefully. The sum as I goes from 1 to n, I n plus 1. Sorry, that's a little illegible. So all transpositions ending on n plus 1. And that sum of transpositions centralizes Sn inside Sn plus 1. So it gives me a bimodular endomorphism. Okay? And then again, it's a cool little calculation to check that the degenerate affine Hecke algebra relation holds. You might recognize these as sometimes called Eustace-Murphy elements. And so, okay. Okay. Let's keep the theory there. Okay, so now we've got a pivotal monoidal category, and we've got a module category. And so I'm trying just to illustrate these ideas with these hopefully appealing example. I want to illustrate this final idea that I told you at the beginning today, that the center of that module category should be a module over the trace of the monoidal category. So we're just going to talk about those things for the last few minutes. Okay. I mean, I think you all know what the center of that module category is, in some sense. Actually, I don't think I know really in any sense, but it's just the direct sum of the centers of the group algebras of the symmetric groups. So at least it has a basis given by conjugacy class sums. Conjugacy classes in all symmetric groups are parameterized by all partitions. So it has at least a basis indexed by partitions, like the algebra of symmetric functions. And I'm not, I mean, these centers, this is just saying that the center is a module over the trace, but of course the center is actually a commutative algebra. And this statement says nothing about that algebra structure. But in my experience, this is an amazing tool for actually being able to get at that algebra structure by kind of moving around between different blocks using this action. So I'm not saying anything about algebra structure, but that's kind of one of the remarkable things you can do. For example, I think you can use it in category O and prove that the centers are cohomology algebras of partial flag varieties and stuff like that. So, you know, I'm not sure. Okay, so, but I'm forgetting that this is an algebra and just telling you at least how to make it into a module. So I need to mainly tell you now about the trace. Of Heisenberg, right? So we've got this module category, and we didn't know a whole lot about this center, but at least we had a basis. Well, you know, we know a bit more than that, really. But okay, so so now to this trace of Heisenberg. Yeah, maybe I'll say something, but it's probably not what you wanted me to say. But, you know, there is a nice theorem there. Let me tell you that. I mean, I'm going to use your question to say something else I thought I might say, but it's probably not answering your question in any way. But I think we've got a couple of minutes to do it. I mean, one way of once you have some interesting monoidal category, one way of constructing module categories of it is simply by taking quotients of it by left tensor ideals. So in fact, in this situation, there's a little theorem. So I have this Heisenberg category, and it acts on modules over the symmetric groups. I should probably I put finitely generated projective modules. It also acts on that because induction and restriction send projectives to projectives. So this is our monoidal functor coming from this action that we've constructed. And then you can do a very stupid thing. You can this is functors and natural transformations. You can evaluate on some object And if you evaluate on the trivial S0 module, S0 is just the field, so you evaluate on the trivial S0 module, so you evaluate functors and you evaluate natural transformations, you end up just in this category. Just finitely generated projectives over all. And so this was monoidal, but very importantly, this is not a monoidal functor. This is just some evaluation. It's not a monoidal functor. And so this is kind of amusing theorem a little bit. So that gives you a functor from Heisenberg to projective modules over symmetric. This is characteristic P, but totally okay theorem as well as characteristic 0. That category on the right is Karoubian, so by the universal property, it extends to the Karoubi envelope. And the kind of kernel will be a left tensor ideal here, because this is you can compute exactly what left tensor ideal it is. It's exactly the left tensor ideal generated by that morphism. Just the dot on the upstrand. Remember, upstrand was induction, and if you look at induction from S0 to S1, this Eustace-Murphy element is 0 on that one. So this is certainly in the kernel, and the content of the theorem is that the left tensor ideal generated by that is exactly the kernel. And so you get this equivalence of categories between this quotient by this left tensor ideal and this is kind of amusing because this is just some bunch of finite dimensional algebras. This is some finite dimensional category, which is not a direct sum of finite dimensional algebras in any way. It's okay. That was maybe just a sidetrack, which definitely didn't answer your question, did it? Okay. So I've got to now tell you the trace of Heisenberg. Remember, this is some algebra. And I'm actually not going to tell you very well what the trace is. I just want to give you a glimpse. And I want to put this central charge -1 Heisenberg into the trace. Now, I'm at least going to give you the map, so it at least looks plausible. So I need, in here I've got these PNs and QNs. I need to tell you what trace classes Pn in this Heisenberg goes to, what trace class Qn in this Heisenberg goes to. And this is, you take n strings, so that's the n cycle, right? Let's just call that n cycle. And take its trace class. So that just means kind of close it up around that hole. Oh, yep. Yeah, it's kind of amusing. I'm not lining my... Okay, that was a bad picture, but there we go. Okay, so that very clumsy notation for the trace class of the upward n cycle. And Qn is the same, but with the opposite orientation. Let's just, really, let's just do P1 and Q1. Just the general calculation is not really any harder. And see what we can do here. So I at least want to convince you that this is all plausible. That's the relation that we've got that we're after, right? For this level -1 Heisenberg. So I'm going to compute that those trace classes satisfy that relation. So P1, Q1 is that. Remember, this multiplication in trace is like sticking one inside the other. And that top relation here tells me that up, down, I can kind of pull the strands past each other. And haven't I got up, down? Yes, I have. Up, down. So I can pull these strands past each other. There's my hole. Up, down. That's equal to that by that relation. Now we're in the trace, so we can kind of shuffle this around the picture. And that has the effect, if you think about it, of switching the orientations when I wrap the top crossing around underneath the other one. Okay? And so now I've got this down-up strands. And how do you pull down-up strands past each other? Well, that relation tells you how to pull a down-up strand. You get the identity minus that pair. So it's not a really very exciting punchline, but it's what I came up with. Minus that, and but now this tongue I can wrap it round again, right? And it just becomes a bubble, a counterclockwise bubble, and the counterclockwise bubble is just the unit. So that is exactly PQ equals QP minus 1. Okay, so I mean, that was a very trivial calculation that I just made, but you can do it for Pn and Qm, and you exactly find these Heisenberg relations. And so this trace has this infinite dimensional Heisenberg sitting inside it. It actually also has a Virasoro algebra sitting inside it, and I'm just going to write down what it is. You have to kill some. You have to make some central specialization, which I'm not going to tell you about. So this is a nice theorem of Kautis, Lauder, Licata, and Susson. It's reasonably recent where they made this computation, and it's quite surprising that this infinite dimensional algebra, which kind of appeared. I don't really know what W1 plus infinity is, but it contains an infinite dimensional Heisenberg and an infinite dimensional Virasoro in it, both at once. Suddenly you're kind of getting to some kind of, out of something surprisingly naive, you're discovering some very interesting algebra. Okay, so... so
their statement is that this is the complete trace.
This is the complete trace, and all I've given you a glimpse of is how at least the Heisenberg sits in it. But there's more. There's this Virasoro part as well, and together they give you this W1 plus infinity algebra. And so now we've got to finally come back to this action of the trace of Heisenberg on the centers of symmetric group algebras, right? Because that was, and so what module could this possibly be? Well, in particular, it's a module over Heisenberg, and it's exactly this Fock space representation that I introduced. In fact, that is easy to prove, at least when we're in characteristic zero, because I mean, this is this sort of irreducible universal module, and the vacuum vector. So let's at least check that the Q's. So the Q's were the trace classes of well, okay, I'm going to do Q1, but it's the same for any Q. It was the trace class of the counterclockwise bubble around the hole, and then in the hole you stick your element of the center. Let's put the Let's put the 1 in the symmetric group S0 in there. That's definitely central in the group algebra of S0. So I'm going to put in a 0 there, which tells you it's S0's trivial module in there. I could put any positive integer in there if it was the unit of Sn. So this is induction. So what symmetric group have we got to be at here? Oh, S minus 1, which is, that's definitely 0, right? So all the Q's are 0 on the unit object of S0 for that very stupid reason. And the central charge is correct, and it's not 0. And so we get, by the universal property of this Fock space, we get a homomorphism from Fock space to here, and this is irreducible. So it's injective. Oh, but they both got the same dimension because they both have this basis by partitions. And so that's how you see that. And of course, actually, you have to prove that to prove this in the first place. But okay, that's a good point to stop. Yes, I did, but I don't know very much about it, and I can't remember the definition. But you find it in Coutis, Lauder, Licata, and Sussen. They don't work with these generators of Heisenberg. They work with some other ones that give you the right integral form.
Why you said that the trace of the Heisenberg vector is UH minus 1? Is it just an embedding or an add-on?
The trace is actually this bigger algebra, which contains the Heisenberg, but it also contains this Virasoro. And so that's merely an embedding. But actually, you look at this and you discover this Virasoro. It suggests there should be lots more connections in this. As I say, I always thought this notion of trace was sort of not very interesting, but suddenly in this monoidal setting, it's quite startling. And I think it was a well-known action, which I think actually it was Igor Frenkel and Wei-Chung Wang in like the 90s already had constructed that Virasoro action. But this makes it. This is a machine. It's very. You just look for you just try to present these categories of endofunctors and natural transformations for your favorite categories, and then you can just pull in all these tools.
For other values of C, do we know some other interesting representations of categories?
Yeah. There were these higher level cyclotomic quotients of affine Hecke algebras. There's actually a very strong connection between the. So Kavanagh only looked at this Heisenberg minus one because he was exactly calculating the relations between induction and restriction functors for symmetric groups. But now we have these Heisenberg categories in all levels. And in fact, there's a very strong connection between them and Kac-Moody-2 categories for the Lie algebra, SL infinity or SLP hat, depending on what field you're over. And actually, these remember, this Heisenberg, it's this principal Heisenberg subalgebra of some affine Kac-Moody algebra. And this actually has a categorical version. These monoidal categories have a completion, which becomes equivalent. And so it's like a cheap way to tell you about Kac-Moody-2 categories because Heisenbergs are much easier to introduce. Okay.
So is it possible to have vertex operators?
I don't know.
Have all those sheets?
Yeah, I don't know anything about vertex operators. Oh, I should have said that. That's very important. So there's, in fact, let me even write it. Somehow I was getting carried away with my traces, but the first thing Kavanagh asked when he defined this category is what is K0 of his category. And he constructed an embedding of Heisenberg in there, and I muttered about taking these trace classes of taking the isomorphism classes of up and down being P1 and Q1, and so it's this Kavanagh conjecture that this embedding that he constructed in his original paper is actually an equivalence of categories, and it's still an open conjecture, and it's kind of challenging because we've left the finite dimensional world here, and so it's still been resistant. On the other hand, the trace is good. So we could do the easier thing, not this harder thing.